Okay, welcome back to, is this lecture 16 or 17?
16.
16, okay. It said I had already created 16, but that might have been a boo-boo. So this is Wireless Without Batteries, lecture 16. And today we're going to talk more in depth about balanced coding. How do you make a balanced code? This is for backscatter modulation. As I was telling the class here, you just have a proposal for the distance learning students. You have a proposal due to me on Wednesday for what your project should be. That proposal, quote unquote, is really just send me a short paragraph about what topic you want to pick for your final term report, which you'll be doing towards the end of April. And the project statement, hopefully everybody's seen it, it's been posted online. I know I handed out paper copies here in Atlanta, but if you didn't get one, the actual project statement is online available. And I should have all the updated readings as well up there. The reading that this lecture comes from here is a paper I published back in 2015. I went ahead and put it up there. It's a nice set of notes for how a balanced code works. Okay. Now, we talked a little bit about what a channel code is last class period, and we talked about a couple of well-known copies, well-known versions of channel codes that have been incorporated into protocols. For example, F2F, frequency double frequency, which is what early generation RFID as well as like magnetic stripe cards use to encode information. In this case, that was where you basically sent something like this to represent a 1, and then double that frequency of square wave to represent a 0. And so you can think of this as basically having, one way of thinking of this is having 4 coded bits for every 1 data bit that you send. And well, the nice thing is that if an uncoded bit stream unfortunately places the bulk of its frequency content at f equals to 0. So the baseband spectrum would look something like this sync squared type of pulse when I'm just going back and forth. And unfortunately for backscatter, that's exactly where you do not want to put it. For a lot of these AC coupled media, not just backscatter, but AC coupled media in general, this is a forbidden region for information because it's going to get notched out in a filter, or there's going to be too much noise or interference in that area. And so F2F is nice because we say that each of the code words are balanced, that is the same number of 1s and 0s, if we view these as coded words. And that means that the signal spectrum is going to look more like this. It's going to have a null. Anytime you make a data signal that is constructed from balanced code words, you will get a frequency null at 0. And then the signal kind of does its thing over there. Okay. Now, F2F is not the best idea in the world, though, because if we are concerned about power consumption, we said in this class, when you go to send data bits, or when you go to do anything with synchronous logic, and by synchronous logic, I mean logic that is driven by a clock. Lots of different kinds of ways to drive logic by a clock, but that's most of the logic that you're familiar with, right? Everything in your computer, your processors in your phones. These are all examples of synchronous logic because there's a clock keeping beat running the processor at a constant clip. Now it turns out that for CMOS logic in particular, but generally in all logic, holding a state between clock cycles takes very little power. Why? Because there's so little leakage current in most of these devices. Only now, when we get down to like 14 nanometers, are we actually seeing that leakage current actually is starting to become a significant factor compared to the current that it just takes to transition to a state. So for that reason, if once you have a fixed number of devices in a synchronous logic machine, the power consumption winds up being almost exactly proportional to the clock frequency. And this explains kind of why we can't clock beyond a certain frequency on our computers, right? If power consumption ramps up is proportional to clock frequency, but the device isn't changing size physically, then there only comes a point where I clock it so fast. Beyond that point, I just have too much heat in my circuit, my chip. So one of my power colleagues, Professor Habitler, explained in a meeting one day when there were some computer engineers that he was getting very frustrated with them. He says, "You're using all this power, but you're not doing any work. You just have power in. Nothing's happening to it. So of course it's going to turn into heat." And that's the only place for it to go. So and this is actually true for low power devices too. The faster you clock, the more power you consume. So when I look at something like F2F, you think, well, that's sending 2 or 4 bits for every coded data bit. If I want to have a tiny little node that harvests energy and sends back information on a backscatter link or an inductive link or whatever kind of link you can concoct, if I don't have any RF components which tend to dominate the power consumption, and it's only the baseband digital components that are dominating power consumption, then the fewer clock cycles it takes to send data, the better things will be. So this gets into sort of this topic, this theme of the entire class, where we're not just looking at communications from a point of view of trying to push bits across a radio link as fast as we can. We're actually being very mindful of the power that we consumed, because we either don't have it or we're trying to be very stingy about using that power. And so, one of the things I need to figure out ultimately, if I offer this course enough times, it'll be permanently listed. We got to come up with a name for it. And right now it's called wireless without batteries, because that's the only thing I could think of when I was filling out the paperwork a couple years ago. And it was kind of interesting. It kind of piques people's interest to think you can do radio without a battery. But at the end of the day, this is one of the problems when you deal with a fairly new discipline whose boundaries are sort of malleable or not very well established yet. What do you call it? What do you call it? And so I don't know. I'm working with all these. At one point, I was thinking, well, what you could call it? Wireless forever, because the whole point is to never have wires connected to it, not for charging, not for. I said, well, that sounds kind of corny. And so then my latest thing that I've been thinking of is, well, what about cyber physical radio? Because we're dealing with radios that are optimized for this world where you have lots of tiny little devices that are sometimes using the communications channel for power as well as information and for sensing and for other things. How do we design that physical system? That's really what this class is about. And so yeah, maybe that'll be part of your last homework assignment. Is think of a name. What would you like to call the course? Because there's no textbook in it yet, right? We have to write the textbook eventually. Anyway, enough of that rant. All that to say, F2F, 4 coded bits versus 1 data bit. If we could somehow get that ratio down, we cut it down by a factor of 2. We've doubled the power savings. We've cut in half the amount of energy per bit we need to send. So in later, we also studied last class period FM0, which we said was really just a variation of something called Manchester encoding. And in FM0, you basically send ones get transitions in the middle, Two zeros get no transitions, but you always have a guaranteed transition wherever there's a data bit change over the boundary of data bits. So these are all guaranteed transitions. I always said that that was really just another way to send Manchester data, which is, if you were to encode these exact same signals, you just wind up putting your guaranteed transitions in the middle. Because that is actually a very old way to modulate data that harkens back to the 50s and 60s when people had to build digital communication systems out of discrete transistors and that sort of thing. And there was no real good way to make a disciplined oscillator that was portable and simple. So as a result, you had to make signals that had a nice guaranteed transition at regular intervals, because your signal wasn't just providing information, it was also providing the clock that you'd need to decode and logically operate on the signal. So if you imagine you were a receiver receiving one of these signals, you say, well, there's going to be a guaranteed transition every other coded data bit. So all I have to do is just sort of look on that and kind of keep time with that transition, and I can recover the clock in that regard. But you'll notice that one of the problems with this is that you still have two coded bits for every one data bit. And then this begs the question, well, you know, how do I can I go any further? Can I reduce it further? If you look at information theory, all we're actually trying to do is get rid of the DC component around what is otherwise a sinc squared type power spectral density. And we're limited in what we can do because we have something like a backscatter network where we're just load modulating, switching between two binary different loads. So all we have are square waves, sharp transitions. How do you make something smooth and do all of your signal processing tricks and pulse shaping tricks when you just have sharp transitions? It's kind of counterintuitive that you can do anything like that. So what we can do is there's a whole field of coding theory involving channel coding for communications or recording media, where a lot of work has been done. And a great resource for this is a book by Keys and Mink. I think it might even be available online. You can do a search for his name. But this is a whole entire book on recording codes. These are codes that are used to write to optical discs or to hard drives or to tape memories and things. So a lot of it's kind of dated. Some of these modes or media of communications or recording bits have been deprecated over time. Nobody saves things on a tape recorder anymore. And even magnetic media are becoming less and less common as we kind of exchange them for flash and all these other forms of memory. But you probably didn't even realize that the data bits that are being written to these devices are not the actual data bits that you send to the devices. There's additional level of channel coding that goes on to balance the bits so that they go across the communications medium reliably. And it turns out that balancing bits is actually a really nice way to do error detection as well. Because like anything, even though it's going from your CD to your optical LED reader that's only a few millimeters away, that still constitutes a wireless communications channel, and data can be corrupted because of noise and whatever other problems that you have, smudges on the optical medium. So we don't think of those as wireless communications medium, but they're essentially a wireless communications medium. They need protection, and what's more, they need error detection. did I actually read the data correctly? So if I have a balance code where, let's say, I transmit the data 1, 1, 1, 1. Well, that's not a very balanced data. So that might encode as something that's more balanced. It would be something like that. This would be an example of, let's see, 5 bits in. I have here 8 bits out. And this would be a balanced code word that I could then write to or read from one of these recording media. Well, what happens if you get one, if you make a boo-boo and you accidentally have a 1 there? Well, it turns out that balanced codes are nice because it automatically does your error detection for you, right? You look at that and you say, wait a second, this is supposed to be a balanced code word, and I now have 5 1s and 3 zeros, so clearly I've messed up something. So if I have a fairly light a communications channel that produces fairly few errors, this is a great way to do error detection, because I would actually have to make 2 errors, and not just 2 errors, but 2 very specific kinds of errors, coupled errors, in order to make the kind of mistake where the code word would balance again. And this is actually very good for optical medium, because it turns out that for things like compact discs and DVDs, you can really only make one kind of error, right? You can go, I forget exactly which the polarity is, but you can go from 0 to 1, but you can't go from 1 to 0. You can erase a bit, basically, but you can't go the other way just because it's based on reflective light. You're not actually going to reflect the light in the right direction. And so for that reason, that almost constitutes a foolproof use of balance codes, because you get a balanced code word off there. You can only go from 0, you can only change zeros to 1s in that medium, not the other way around. So any combination of errors will always result in a detectable code word. So that's the idea behind a balance code. And so how do you construct a balance code? Well, first you need to figure out, what size that code that you want to use. And here in something like RFID or backscatter communications, you're generally more limited than you are in, say, making a device for a hard drive that encodes and decodes data. Because here are sort of the 4 areas of concern when you benchmark different types of balance codes in something like an RFID or a sensor mode. So one of those areas of concern, of course, is cost or complexity. If I have to have a system that needs a big table lookup to implement the code, then I'm going to burn thousands and thousands of devices implementing this table lookup, and that's going to take power consumption. But it's also going to make my circuit bigger, and it's going to make it more costly. In the world of small chips and devices, complexity translates almost directly to cost. Let's say I have a wafer of silicon. Well, what happens when I go to make a device? I got to go to the foundry and say, here's my masks. I want you to start cranking wafers of silicon off your fabrication line. And we'll cut it up and turn it into chips, package them, and ship them out as product. Well, what are they going to do? They say, well, we're going to charge a huge fee to set this up, because that's the way that they work, right? Well, once they get the thing rolling, the actual silicon wafers don't really cost that much. There's a fixed price involved, and what's more, the more devices you get on that wafer, the lower the cost per chip becomes. So if I have to double the number of devices I need to implement some sort of fancy coding scheme, then I just double the cost of my chip by following that logic, right? So we have to keep that necessarily low. Of course, power consumption is a problem here. We want to consume as little power as possible because that's the name of the game. We want to send data with using minimal amounts of power. And then link performance and throughput. Those are two other areas of concern for us. Does the code actually work through the channel of interest? And can we send the most number of data bits per coded bit? And balance code. So for that reason, most of these kind of converge on the insight that we need a short block code for our channel code. Short in that we don't have that many inputs and don't have that many outputs. So the coder you can implement in some sort of hardwired configuration instead of a table lookup, which in hardware would take tens of thousands of devices to implement. And by block code, we mean it's fairly simple to construct in that you have a small number of input bits that produce a slightly larger number of coded bits. Then you can make a tag that codes its data very efficiently. And so let's explore this idea a little bit more, how to make a block code. So let's say we start with k number of coded bits. And L will be the number of input data bits. So I have L number of bits, however this turns into, I run it through my encoder, and it produces K encoded bits. L in, K out. Where of course K always has to be greater than L, or else I'm not adding any redundancy and I'm not going to either don't get the desired properties that I want or I start losing data. I lose data when K is less than L, right? Now it turns out there's a beautiful theorem in combinatorial analysis that says the number of balanced code words M in a k-bit code book satisfies the following equation. M is equal to k factorial divided by k over 2 factorial quantity squared. So let's see how that works. Let's unpack that for a second. First of all, if you have k bits, there should be 2 to the k bit combinations, right, that you can arrange. M is the number of those bit combinations that have the same number of ones and the same number of zeros. Let's just test this theory really quick. Let's say we have k equals to 4. Okay, how many code words should exist in there? There should be 16, right? 16 code words. 0, 0, 0, 0, 0, 0, 0, 1, all the way down to 1, 1, 1, 1. That's 16 possible states with 4 bits. If we look at the formula here, we have m equals 4 factorial, so that's 4 by 3 by 2 by 1, divided by k over 2, 2 factorial. Yeah, so that should be 2 times 1, and I got to square it, so I got 2 times 1. So m is equal to 6. Is that true? Let's go ahead. This is the only time I'll do this all out by hand because it's a good exercise. Let me be systematic about this. Okay, let's see. Are there 6? Can we find 6 balanced codes here? Start. This is balanced, got the same number of zeros as ones. This one's balanced, this one's balanced. And then, of course, the counterparts, the complemented counterparts. This one's balanced, this one's balanced, and oh, this one is too. You see, each one of these is actually the complement of the other in the other column. That's a complement, and that's a complement. So yeah, it turns out this beautiful little formula works no matter how complicated the code words are. If you had a 500-bit code word, you could plug this number into here. You'd have a hell of a time calculating factorials, but you would be able to compute the exact number of balanced code words. So this kind of suggests a really interesting way to construct a code book. And so what I have, let me go ahead and switch to this PDF paper here. Oops. I just opened up one of the, there we go. So, as an example of what this might look like, here's an example data sequence. This would be a rate 4-6 balance code. So if we go back to our notes and say, well, let's see if we can calculate this factorial. M is equal to 6 factorial. So we're going to have 6 bits on our coded output. How many balanced code words should there be? Well, it should be 6 divided by 2 factorial, so that would be 3. Notice that you can't plug odd code bits into that formula, otherwise you'd have like 5/2 factorial. Why can't you put odd number of bits into that formula?
Because you're going to have balanced codes.
That's right, you're always going to have one odd man out, poor odd bit out. There's no way to balance an odd number of codes, so it's convenient that the formulas don't work either, right? So 3 factorial in the denominator, taken twice. So let's say 6 times 5 times 3, or times 4 times 3 times 2. 2 cancels. I'll cancel 2 out of there. Let's see, I can cancel one of these 3s. I cancel one of these 3s. And so I should get 3 times 5 times 2. There should be 60 code words. Right? No, 30, right? 15, 3, 20. Did I over cancel something? Oh, you're right. This should be 2, not 3. There we, whew. Good. 20 code words. Now, if I just want a simple set of code words, in other words, I have to have, what do we use as the variable? L input bits. And it maps to k-bit code words. I have to have 2 to the L combinations to select into those k-bit code words, right? So for that reason, if I want a really simple code, I can't use 20 code words. I have to use some power of 2 code words, right? So I could have 4 input bits where L is equal to 4, and that can map into 6 output bits, where K is equal to 6. I can't make L equal to 5, because that would give me 2 to the 5th, or 32 input states, and there wouldn't be enough balanced code words to uniquely assign to those inputs. And I could and if I go down to L equal 3, well, that's a waste of time, right? Because I'm not using all of my code words that I possibly can. I'm decreasing my real data throughput. So as a result, if I have 4 input bits, got it backwards, L, that has to go to K output bits. Now, if we go up to 6 input bits, we can produce 8 output bits. What we're really saying here is that L is equal to the lowest common integer of log base 2 K factorial over K halves factorial quantity squared. So I'm going to take a break right here, but I want you to compute really quick. What is L for K equal to 10? And then we'll come back and I'll resume the recording. Okay, what did you get? What should L be? Yeah, this is, what did you say it was, Buzz? That's the right number. 252. Ah, so close. 252 states. It should have been 256, right? Then we could have 8 input bits. 2 to the 8th is 256, but alas, there would have to be 4 ambiguous states. And so we have to crank this down to 7. Oh, so sad. And if we did 12, this would be 9. And so look what happened here. And then if this was 14, we could get away with 11. So it's interesting that what you see is a very common principle in coding theory at work. It doesn't matter if you're talking about error detection codes or balance codes or forward error correction codes. We're going to be talking about that in the satellite class for some of you that show up into the satellite class too. It doesn't matter. The more complicated you make the code, the better it performs in terms of throughput and redundancy, right? We started out with 4 here, and then we encoded that with 6. So what's the, if we had the ratio of K to L, that's basically going to tell us our redundancy ratio, how efficient our code is in terms of throughput. Well, this is 1.5 here. And going from 6 to 8, that's 8/6. That's going to be 1.67. Ooh, starting to get very efficient. But then it drops back down again to 10/7. I don't even remember what the ratio is here. Let me take a look here. I don't divide by 7 enough to remember what that is. Now it's down to 1.43. We're losing ground. 12 divided by 9. Well, now we're back at 1.33. And 8 divided by 6. I didn't get that right. That was 1.33. So you see, we have to go all the way up to a complicated 9/12 codebook just to recover the same data rate that we had with the simplified code word. And then only after we get to 14 bits do we get something that's actually an improvement in terms of throughput. 14 divided by 11, a slight improvement at that, a ratio of 1.27. So just out of curiosity, now let's go over to the paper and take a look at some spectral plots. Here's an example, first of all, of data bits and coded bits. This is with the rate 4/6 balance code. Here's my data bits coming in. You notice I've got a couple of sequences that I've broken it up. I've got some runs and some biases in this data. Look at that long set of 7 zeros. Ooh, look at that equally long set of 8 ones over here. But when each of these is coded according to that 4/6 block code, look, each of these coded bits is balanced. And the most run, what's the biggest run that shows up in here? There's 2 zeros, 2 ones.
Maximum is 2.
Yeah, maximum is 2 in this instance. I think there are maybe some pathological combinations where you could get like 3 or 4 across the boundary. But for the most part, this data sequence will have no DC content whatsoever. And that actually shows up in a nice spectrum plot. Let's take a look at the spectrum here. See if you can see this. This is from the paper if you're having a little trouble seeing this on the screen. You guys are probably fine. The distance learning students I'm not so sure about. So this dark line here, actually do you see the dotted line here? That is actually the Fourier transform of the PSD of a simple uncoded data stream. Ones and zeros, backscatter modulated without any coding, runs and all. You'll notice the peak occurs here at 0 frequency, and it falls off, and of course beyond this point it will pop back up again, and you get those little sync squared type side lobes at higher frequencies. But that's our baseline. That would be a rate of 1-to-1 coding, right? Every real data bit is a coded data bit, because there is no coding. And everything's normalized to that rate of frequency so that we're comparing apples to apples, right? We want the actual coded data frequency to be the same no matter what, because that'll tell us that we're consuming the same amount of power. Okay, now Manchester encoding, or FM0, that's this solid black line. You see that puts a really nice null down here deep. And when you normalize to the same coding frequency, it puts the bulk of the frequency content somewhere between 0.3 or 0.4 of the actual coded data. Now that rate 4/6 code, which in the back of the paper there's a whole table of what these codes would look like when they're implemented. Here's the inputs, 4-bit combinations on the input, 6 combinations on the output. You see that one, look at what happens. What that increased data rate does is it pushes some of the spectral content closer to 0, but it still keeps this scooped out here in this region. And if you see the rate 6/8, that's this green dotted line here. It's kind of hard to make it out. But it comes down and falls off the table right around here too. So again, no DC content. You've evacuated this signal spectrum here by balancing the code in that regard. And then you keep going up and up in complexity. Here's the rate 9/2 one, the rate 11/14 one, that's the red line here, rate 7/10, rate 9/12. Increasing complexity allows us to evacuate more and more spectrum here, but keep the overall shape of the spectrum untouched. You see, as you increase the order of the coding, it starts to look more and more just like regular old BPSK, just with this chunk removed here at DC. And I have another plot here, a logarithmic plot. which you can take a look at as well. It's that exact same plot, except now we're showing frequency, logarithmic frequency on this axis, and then logarithmic power spectral density on this axis. And see the uncoded BPSK or uncoded signals? That starts here on the logarithmic axis, looks very flat, and then starts falling off the table, boing, boing, starts getting those side lobes right after that. Here, all of these dive towards 0 on this log-log plot. But you'll notice that there's a couple of interesting code books, that have this sharper edge to them. So solid black line, again, that's Manchester. And then I've got my rate 4/6 here, my rate 7/10, my rate 9/12, my rate 11/14, my rate 6/8. These all dive with this kind of 1-to-1 slope, because these have, when you look at their power spectral density of the signal that you make with this, you can view this as having a Taylor series, right? About 0. You can expand this and call this A. That's my DC term. Plus, there's a BF squared. Remember, there's only even components to a real valued power spectral density. So I should have some expansion like this. And what that balancing does is it always gets rid of A, my DC component. So I always get 0 at X evaluated at frequency equal to 0. However, you can play around with the codes, and it turns out that a subset of those balance codes actually also get rid of this component. And a subset of those, for a very complicated code, will get rid of this component. So you can actually make very, very deep nulls by playing games with these balanced codes. And that's actually what this graph is showing. So you'll notice that here we have a rate 3/8 code. Remember, we had a, if you have 8 output bits, you should be able to make 6 input bits. There should be at least 2 to the 6th states that you can accommodate with that. But it turns out that there are, if you look here, here's an example of 2 to the 3 or 8 possible code words within that total set of 60 some code words that actually have this interesting property of extra nulling at DC. So all of these code words have, if this column says 2, this bow column, that basically means that it's up to F squared has been removed in the power spectral density of that individual signal. And then there are some code words here that actually have balance order of 3. That means you've actually gotten rid of F to the 3 or F to the 6 in the power spectral density by using just that signal. So it's interesting the shaping that you can do. So that's why, if you look at it, the slope of these other, what would look to be suboptimal codes, like the 916 or the 3/8 or the 512, they're not as good as the just using all of the balance code, but they dive more quickly. And so if you're in a channel that has that you need a very deep null, that's an alternative way to send your signal through without distortion. So anyone have any questions about that so far? Comments? Yeah, Mulian.
About the balance, why it needs to be hard-coded into a balance code?
Why does it need to be hard-coded?
Why it needs equal numbers of zeros and ones.
So you don't have to have an equal number of zeros and, well, so why does it have to have zeros and ones? Because if you have the same number of zeros and ones in your output code words, then you can guarantee that your signal spectrum has a null at DC. And that's important for what we're doing, because if you're modulating backscatter, whether it's using inductive modulation with an RFID card, or if you're modulating on a far field RFID tag or backscatter sensor, what's going to happen is you have a carrier frequency here with a carrier and that dirty noise that goes along with it that's always along for the ride. If I use balanced code words, then regardless of how my signal spectrum looks, I know that this area in here is going to be empty spectrally. And so that means that I can decode the signal with minimal problems. I'll get the maximum sensitivity, the farthest range in that scenario. Now, I don't know if anybody's interested in doing projects and if we have any digital types and coding theorists for projects, but there are a lot of interesting variations you can take on this, like analyzing how complicated the hardware you would need to implement one of these codes, hardwiring versus table lookup. That's an interesting study. The average RFID chip, for example, uses about 60 to 80,000 devices on it. How high can you go in the table before it becomes untenable to implement in hardware? So if you hardwire some of these codes up, you may find you need 2,000 devices. Oh, that's not bad. It's just a small percentage increase. Probably doesn't reduce the yield of your chip manufacturing. But then if you do a table lookup implementation, you might need 6,000 devices. Well, now we're starting to increase the device size, possibly the power consumption, and you have to worry about that. What's the optimal here? That might be an interesting study. And there are all sorts of interesting techniques you can study. For example, this is not very practical for the types of communications networks that we're studying in this class. However, one way to balance a signal is called Knuth coding. Donald Knuth was a famous professor at Stanford University. And he said, well, let's say I have a very unbalanced bit sequence that I'm sending. There's a way to make a block code very simply without a lot of overhead. I said, well, okay, how many bits do I have there? I conveniently drew 12 bits. It says, there's always a point somewhere along that code where it may be the first bit, it may be the last bit, or the second to the last bit. But I can always find a place where if I invert the sequence up to that point, I can get a balanced code book, or a balanced signal. So, if you think about this sequence, let's figure out where this would happen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of the 12 bits are ones. So what I need to do is to flip this. And I think if I flipped it up to this point, did that do it? Oh, I went too far. If I flip it up to this point, one, 2, 3, 4, 5, 6 zeros, 1, 2, 3, 4, 5, 6 ones. So I would encode this as a 6. If I flip to position 6, then I have a balanced code word. And then what I can do is use Manchester encoding to encode that same number up on the front. So the number 6 in binary would be 1, 1, 0, and Manchester encoded that'd be 1, 0, 1, 0, 0, 1. So look, I added redundancy just like any good coding would do. And for this crummy example, and I really should have done 16 bits, right, not 12 bits, because I'm now using 6 bits, 3 bits up at the front to denote this. But I've gone from 12 bits to 18 bits. So I'm still doing a lot better than just straight up Manchester encoding in terms of redundancy. I've balanced the bits. Both the preamble I added and then now the data sequence that I transmit itself are balanced. And I haven't increased the data rate very much. And so obviously the more complicated, this is a really nice algorithm to run when you're encoding thousands of bits at a time. Probably, maybe not as practical for backscatter systems. I don't know, you could analyze that technique. Another technique for at least quasi-balancing, nobody's ever dealt with, I don't even have a name for it, it's called flip bit encoding. So let's say you have a data sequence. And let's break it up into hunks. I say, well, let's do an example of 4 hunks. So now every 4th bit, you add an extra bit. 1, 1, 1, 0. Now I'm going to add a bit, and I'm basically just going to put a dummy bit in here that helps balance the signal. I've got 3 1s and just 1 0, so I'm going to put 0. And I go 1, 0, 0, 0, up. I'm going to add this to balance it out. 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, and so forth. So there I've added just a little bit of redundancy, and I could still potentially have runs in this sequence that are long or biases, but I've broken up all the really big ones. And in fact, I could even do this several times. So for example, I could run this through a flip bit order 4 encoder, and then I could take the exact same sequence and run it through a flip bit encoder 7 sequence to kind of remove more DC content. 1, 1, 1, 0, 0, 1, 0. Well, it doesn't really matter what I put there because look, I've got the same number of zeros as ones. 0, 0, 1, 1, 1, 0, 1. I got one extra 1, so I'm going to put a 0. And then 0, 0, 1, 1, 1, 0. And then whatever came after that, if it's a 1, I put another 0. So you could run that 2 or 3 or 4 times, and it would be very simple to build hardware that could keep track of whether you have too many 1s or too many 0s in a sequence, and just append simple bits. So from a complexity point of view, it'd be very low. The real question is just, is this enough content that you can remove from the signal to make it detectable in a backscatter system? And that's a really interesting question to explore. It would make a good project or something like this. So even if you want to invent your own encoding technique, this would be an interesting topic to explore. Now, what we've been talking about so far has been balance coding for the purposes of trying to wring as much throughput out of the network as possible, out of your link as possible. We're minimizing the number of coded bits that you have to add to get it to behave like a balanced signal. An alternative is to employ forms of balance coding that allow you maximum sensitivity. In other words, there you're less concerned by the number of bits that you add, and you're more concerned about getting some processing gain and moving your signal away from the spectral peak. So one very straightforward example, F2F is a great example of that, right? You're basically, one way to view F2F is that you're taking a data sequence, and then you're multiplying it by a square wave, and then another higher frequency square wave on top of that. So one way to help balance the signal on a UHF RFID tag, and here I'm talking about the Gen 2 standard, the one for 915 megahertz that almost everybody uses now, is when they came up with the Gen 2 standard, it was realized that there is no one-size-fits-all coding. That there's a benefit to having selectable types of codes, so that if you were in a scenario where throughput was essential, where you need to maybe count a bunch of tags very quickly, you could use FM0. Well, on the flip side of that, if you want to rather slow things down, you're not worried about counting as many tags as possible or transferring a lot of data out of the memory of a tag, you can specify something called Miller modulation or Miller modulated subcarriers to get a tag that has much higher range, much higher reliability in the environment that you're looking at. So how is that done? Well, subcarrier modulation, binary subcarrier modulation, and this goes by a lot of names. Some people call it binary offset. Subcarrier modulation. BOC is what the acronym winds up being. So people will just call it binary offset carrier modulation. BOC. This is actually very simple. This is very simple, similar to Manchester encoding, just sort of taken to the next logical extreme. So let's say I have a data sequence like this, a 1, a 0, and a 1. If this were Manchester encoding, I would then have a waveform like this, basically just a square wave with transitions twice as frequent as my data, and I would multiply by this to get my waveform. Well, in the generic sense, for binary offset carrier modulation, now let's say I have a square wave that's twice as fast as that Manchester square wave. And I multiply that by my original data sequence. So basically what that means is that I'm basically just going to be transmitting a square wave, and if I ever transition from 1 to 0, I swallow a pulse. Oh. Swallow a pulse at the transition. Otherwise, what I transmit is just a straight up square wave. And so you can do that as much as you want. You can have 20 cycles of transition in between every bit. Spectrally, what is that doing? Well, remember, now I have to transmit or transition multiple times per bit period, which means I'm adding transitions per bit. If I view this as coded data, I have 1, 0, 1, 0, and that's just to transmit one bit. So now back to the case of I'm increasing the transitions per bit, which means I'm increasing power consumption. My joules per bit is going up that I'm using to send data across my link. But the nice thing about this is that, let's say here's my noise profile on my backscatter reader. Is the area that I want to avoid. So if I had a regular system that was uncoded, I'd have this BPSK waveform. Most of the information would be right here in the problem area. If I get too much noise or interference in a conventional communication system, a conventional wireless system, let's say I'm transmitting 1s and 0s across the radio link in a Bluetooth link or a Wi-Fi link. If I had complete control over the protocol and I found my link was too noisy, what could I do to increase the detectability? Well, remember, in a thermal noise limited system, if noise is my limiting factor, what I can usually do is just slow down my transmission. Don't you transmit with this much bandwidth, transmit with this much bandwidth. Because then I don't have that extra noise fall. I can filter out more noise from my receiver. My signal to noise ratio goes up, and now my signal becomes detectable again. One of the infuriating things about these backscatter systems is that you can't do that. Why? Because look at the diagram here. If I decrease my signal rate, what happens is that more and more of my signal concentrates in this area where noise and interference accumulates. My signal to noise ratio gets worse most of the time in that scenario. Not better, like it does in a regular wireless link that has nice additive white Gaussian noise that's limiting communications. So what the subcarrier modulation does, allows you effectively to slow down your data rate. You're exchanging power consumption for fidelity in your data signal. So this green signal down here, for example, well, the spectrum of that signal will look kind of like this. There'll be a peak here and then a peak here, well away from my noise in my subcarrier. And the more transitions I add, the farther it gets away from the peak relative to the width of those spectral pulses. And that makes the signal to noise ratio go up. So this is the way to play that game where you slow down your transmission and get better signal fidelity, but you have to do this subcarrier modulation. So for that reason, just to explore an existing standard, the Gen 2 standard actually has 3 additional modes of modulation other than FM0. There's Miller modulated subcarrier 2, Miller modulated subcarrier 4, and MMS 8. So the first thing in these other modulations, the first thing the tag does is that it Miller encodes the data. Okay, so what does Miller modulation mean? What does that mean to Miller encode? So first you take a series of 1s and 0s, and then if it's a 0, you hold the state. And if it's a 1, you make a transition halfway through the period. And then, where the modulated subcarrier comes into play, is that you multiply by a square wave that either has 4 transitions per bit for MMS2, 8 transitions per bit for MMS4, and then of course 16 transitions per bit for MMS6. So what that winds up looking is that it's basically subcarrier modulation, where again the signals are just pushed over to the edge. But this Miller pre-coding kind of distorts the signal and actually gets a little bit of extra signal strength away from DC. And that's really all that step does. And so for MMS2, I'll just give you an example here. This comes right out of the standard, which is freely available online. If you wanted to send the sequence 0, 1, 0, what it would look like is that with a guaranteed transition here, then a gap there, and then another guaranteed transition. So you can see each of these intervals is clearly balanced. You have 1, 0, 1, 0, 4 coded bits for every encoded bit. You'll notice that the zeros aren't always the same because of the way this is encoded. This is actually the complement of this over here. These are both zeros, but they're transmitted as a complement. And in doing so, you get these spectral peaks that are away from your problem area in the middle. F equals to 0 in a baseband representation of your signal spectrum. Okay. Any questions? Perfect understanding? I don't want to get into anything else. I'm at the end of my coding theory notes, so when you come back on Wednesday, what I think we'll do is either some applications, or maybe we'll do some surface acoustic wave devices. That's kind of fun, talking about piezoelectrics. Okay, see you on Wednesday.